We present a simulation framework for multibody dynamics via universal variational integration. Our method naturally supports mixed rigid-deformable and mixed codimensional geometries, while providing guaranteed convergence and accurate resolution of contact, friction, and a wide range of articulation constraints. To achieve this, we design an efficient change of variable strategy for general linear equality constraints, a unified formulation based on unsigned distances for non-linear articulation constraints, and a general restitution model based on high-order time integration and Rayleigh damping for arbitrary inequality constraints. Our articulation constraints include point connections, hinges with a controllable rotation range, cone twists, where the rotation around different axes can be separately controlled, and sliding, relative to any objects with a controllable range. This allows us to conveniently simulate a triple rod pendulum, a cloth hanging on a coat rack, a 3-section monocular, boards rotating around a shear shaft with different rotation ranges, and a Nunchaku. Our restitution model supports robust and controllable behaviors for any inequality articulation constraints, not only contact. We're able to simulate perfectly elastic restitution behaviors with our barrier formulation and high-order BDF2 time integration. Then, applying a semi-implicit Rayleigh damping model with different damping stiffness into our optimization time integrator, we're able to simulate different levels of restitution behavior in a controllable way. These novel contributions together enable us to simulate complex real-world scenes in a robust and accurate manner. Here we drop a ball onto a hanging bridge with 10 elastic rods and 40 rigid boards. Here we construct a pulley system with sliding constraints and point connections. Our simulator accurately captures the mechanism of this pulley system when the right end of the rod is pulled all the way down with smaller forces to lift the heavy gold box. Next, we simulate the closing process of an umbrella modeled by coupling a rigid skeleton with a cloth. The skeleton of the umbrella is composed of 13 rigid thin rods, connecting to each other via point connection, hinge, and sliding constraints. Now we simulate a vehicle model with multiple rigid bodies. The vehicle is triggered by a cylinder engine connected to the back right wheel with all other wheels passive. As our system accurately resolves the frictional contact, the vehicle can navigate the terrain smoothly as we pull the piston with a constant force. With a unicycle rolling at different initial speeds, we simulate precession, initial effect only to be captured when accurate frictional contact and momentum conservations are resolved. Our method can simulate 60 ragdolls dropping onto the ground from random initial heights without any interpenetrations. Cone twist constraints are applied here at each joint of the ragdoll with specific rotation ranges, imitating the mechanism of human bodies. Finally, we let the ragdoll take a break on a hanging bed formed by elastic rings and discrete elastic rods. We also cover it with a sheet to keep it warm.